Hello everyone, Mr. Boltri here bringing you video 2.8 where we're going to be talking about centripetal force. To do that, first we're going to do a review of what we learned in Unit 1 about circular acceleration. Then we're going to derive the centripetal force equation and use that to solve an applied problem about a car doing a banked turn. So in Unit 1, we talked about when an object is moving in a circle, it is experiencing a acceleration. Even if it's moving at a constant speed, it's changing directions, so therefore it is experiencing an acceleration because the velocity is changing. So if it is moving with a constant speed, then the acceleration is a centripetal acceleration, which is towards the center of the circle and is what's accounting for the change in direction, which is changing the velocity. Now, if at the same time it's also speeding up or slowing down, then the object will simultaneously be experiencing a tangential component to that acceleration. The actual acceleration vector would be a resolution of the tangential and centripetal components of the acceleration vector. But we also derived a way that we could quantify the centripetal component of the acceleration. Remember, we don't have to remember the whole proof, but there were right triangles involved. So we set the right triangles equal to each other, or did a similar triangles, substituted that into our acceleration equation, and solved for the centripetal acceleration of an object moving in a circle to be the square of the velocity divided by the radius of the circle. So we're definitely going to need to remember this centripetal acceleration formula. It's actually on your formula sheet. So you don't have to memorize it, but you do have to remember what it is and why it's useful. So this is the centripetal component of the acceleration for an object that is moving in a circle. It's the square of the velocity over the radius. So then how can we use that to figure out centripetal force, which is the force that is causing the object to go towards the center of that circle? So we know by Newton's second law that the net force equals the mass times the acceleration. So if we look in the centripetal direction towards the center of the circle, we can say that the centripetal force equals the mass times the centripetal acceleration. And luckily, we already have an equation for the centripetal acceleration, which is v squared over r. So then we can just pretty easily say that the centripetal force equals mass times the velocity squared over r. And then, ta-da, we now can solve for the centripetal force. Nothing much to it. Just yet another application of Newton's second law. Such a useful and valuable tool in our toolbox. So what does this look like in a real example of a car that is turning on a road, which is an example that AP loves to use because it's just so applicable. You could also do a ball that's being swung on a string or anything that's moving in a circle, but I've just seen a lot of examples with cars turning on a road. So the car has a normal force and a weight, and then it is turning to the left, so it's changing its direction, changing its velocity. So therefore, it's experiencing some acceleration. And we can actually determine how big the force is pushing towards the center, which in this case would be the friction between the tires and the road, is the mass of the car times the velocity squared divided by the radius. So the faster you take the turn, the more force is going to be required to maintain the turning radius. Or if you want to do a really tight turn, that's going to require more force because you'll notice the denominator is smaller. Whereas if you take a very large turn, then you can have a smaller force because of the large radius in the denominator. So traffic engineers actually have to use this to calculate, like when you're getting on and off the interstate, you'll notice that off ramps, if you have to like go from 285 to 85, they try to make the radius of those turns as large as possible to require the centripetal force, the frictional force, to be as small as possible. So this is actually a really useful equation. And that's also why you'll notice that when you're getting off on off ramps and stuff, especially if it's turning, they'll have very flashing signs for the speed limit. So you don't want to go over those speed limits because the velocity squared is influencing the centripetal force or the force friction in the situation. So if you're going 10 miles an hour faster than you should, then that's going to require a lot more friction from your tires than actually going the speed limit. So this is a very useful equation and has real practical implications for traffic engineers and stuff like that. So this is kind of the simple example of a car going on level road. But then if you are, for example, driving a Formula One car or NASCAR, then you want to go even faster. So you don't want to slow down. You don't want to reduce your velocity squared. And in some situations, just based on the way that those tracks are run, you have to make some pretty tight turns. So a high velocity and a tight turn is a formula for a lot of centripetal force needed. So besides just having really good tires that have a lot of friction, a lot of racing tracks use something called a banked turn, which is the turn is not level. They actually put a tilt or an incline on the turn, which you can see here. And what that actually does is it makes a component of the normal force also point towards the center of the turn. So we're not relying completely on the force of friction by the tires. We're getting some help from the surface to also push us towards the center of that turn. And actually, there's something called an ideally banked turn, which is if the tilt is large enough, then you can rely solely on the normal force, and you don't have to rely on the friction of your tires at all. So it's just the surface, just the normal force that is causing the car in this situation to turn. So one fun sort of applied problem is, can we solve for this theta? How big of an angle do we need depending on how fast we're going and what sort of radius we want to be turning in? Can we solve for the theta to give us an ideal turn which requires no use of the force of friction? So to do that, first thing I'm going to do is I'm going to divide my normal force into its horizontal and vertical components based on theta. So it has a vertical component of the normal force times the cosine of theta, and then a horizontal or centripetal component, which is the normal force times the sine of theta. And you can do that just using triangles and trying to figure out where is theta and which direction is the normal force in relation to theta. And then you'll notice here I'm using N for normal force and W for weight, which is the same as force of gravity. You could do F sub G or W for weight. We know the force of gravity equals the mass times the acceleration due to gravity, little g, and it is pointing in the downward direction. So now that I have my component forces, I can do the Newton's second law, the FAM law, F net equals ma, in the vertical and the horizontal direction. And I get this. So in the vertical direction, I know that the horizontal component force equals the mass times the centripetal acceleration. This is just a Newton's second law. And then by Newton's first law, I know that if it's not accelerating in the vertical direction, then these two forces are going to be equal in magnitude. They are going to be balanced. So then I have two equations which both have theta, and I want to solve for theta, and they both have this normal force, which is going to be the same. So if I solve the bottom equation for normal force, I can then substitute that normal force into my top equation and solve for theta. So once I substitute in normal force in the top equation, then it's just a matter of moving things around to solve for theta. So I get mg, the mass times the acceleration due to gravity times the tangent of theta equals this centripetal force. And then I can solve for the tangent of theta. I can solve for theta by doing the inverse tangent of v squared over rg. So that is the angle that you would need to use in order to have an ideally banked turn at any given velocity and radius. So that was just one example of an applied problem. You do not need to memorize this formula, but you do sort of need to follow how I derive the formula, because I've seen a lot of FRQs that ask not this exact same question, but because they know that some people out there might have memorized this formula, but they ask a similar question that kind of puts a little twist on this. So you need to understand the steps that I use to derive the formula for the ideally banked turn theta angle. But that's just a little introduction to the centripetal force and centripetal forces for objects that are moving in a circle. We're going to do more examples in our next class. And don't forget, there is a whole unit that is all about circular motion and torque and all sorts of complicated things. So we're going to really dive deeply into that in Unit 4. But for now, I just kind of want to start sprinkling in some stuff about circular motion, so it's not all going to be totally brand new to you when we get there. Right now, this is Mr. Boltri wrapping up video 2.8 on centripetal force. I'm looking forward to doing practice problems with you in our next class. Let me know if you have any questions, and as always, go Bears.